ready for chapter 7. Thermodynamics and Kinetics. Got my fire going. Ready to go and have us a nice little chat on thermodynamics and kinetics, heat. Thermodynamics and kinetics. So thermodynamics, thermo is heat. Dynamic means change. Alright, so what we're looking safety supervisor stopped by. So what we're looking at here is the changes in heat. And then kinetics is all about speed and rate, which is, so these two fields go hand in hand, and they're really looking at whether a reaction takes place, whether it's going to happen on its own, or if we have to accelerate it with heat, or how fast the reaction goes, because on one hand, a reaction that goes too slow is of no use to us, and a reaction that goes too fast, really not much help either. Many times that leads to explosions. So let's jump into our PowerPoint. And so, looking at our PowerPoint, there's not a lot of learning objectives here, but we're going to start off with thermodynamics, the study of energy, work, and heat. So we'll start off with the 3 laws of thermodynamics. And so these 3 laws, energy cannot be created or destroyed, only converted from one form to another. That's the law of conservation of energy. All right, so we've talked about things like that before. Law of conservation of energy. All right, and so that's easy enough for us. It can sometimes lead to a little bit of confusion. We talk about energy lost, energy gained. It's really about changing it in forms. So if we lose it to a form we don't want, that could be a problem. So light bulbs, for instance, now we're switching mostly to LEDs and to other forms of light bulbs, because the old incandescent bulbs got very hot. If you ever had one burn out, you didn't want to immediately reach up and grab it to change the bulb. It would be quite hot. And so a lot of that energy was actually lost. We were looking for light energy, and instead what we got was heat energy for a large part. All right. Where did that energy come from? Well, it was coming from electrical energy. All right. So this law of conservation of energy, energy has to come from somewhere. All right. The second one, the universe spontaneously tends towards increased disorder. You know that. You never have to go in your room and messy it up. You don't ever have to go out to your car and say, oh no, I haven't used it in a few weeks. Now everything has stacked itself nicely in the trunk. Doesn't happen. So everything's trying to get towards increased disorder. So this idea of disorder is a little bit tough to quantify. So how much disorder is there? And so this disorder of a pure crystal, the third law just says, if we're at 0 Kelvin, so all motion has stopped, then if it's a pure crystal, it'll be perfectly aligned. There'll be no disorder. All right. It's only once things start moving that things to get out of the sense of order. All right. And so, so those are our starting points, and we're ready for our definitions. And these definitions, they always gave me trouble. This idea of a system. So the system being what you're studying, and then the surroundings being the rest of the universe. Now, for me, I always had trouble with this as a student, because why? It's kind of vague, right? And so the easiest way to think of this would be if I had a reaction, CH4 plus O2 goes to CO2 plus H2O. And I was doing this reaction, I might study just the energy involved in breaking these bonds and forming them. Oh no, I didn't balance it. Let's balance that real quick. It bugs me. So then 2 here. All right. And so this reaction taking place um, will generate some heat. There'll be some heat left over after I break these bonds and form these. And so we'll talk about that heat going out to the surroundings. But if I were to do this reaction, I might do it in a container. This one's a gas, but if we put some methane and some oxygen gas in here, and then now I also have to worry about the glass on the container, but the heat will still be coming out. And so we could say the system is whatever's in this container. And so then I don't have to try and calculate the glass or any of the heat transfer to the glass. I can just say the heat is leaving it. So the let's say this gets out of control. I didn't put a lid on it, and now the whole table is on fire, right? And so now the table on which my container in which my reaction is taking place might be considered the system, and we can step back and feel the heat from that. And the building, oh no, the building's on fire. Now we could describe the building as being part of the system. And so the system and the surroundings, you have the flexibility to change those to make the math easier. And so what we really care about then is this idea of exothermic and endothermic. And we will be learning, memorizing a few concepts about these. But let's start with exo. Looks like exit. This is heat going out. Endo, heat goes in. All right. Now, this is sometimes shown. If I were shown, going back to my reactant, so let's do reactants, and they go to my products, and we can show heat either as a number or just the word heat on either side. So if I put heat as a product, I'm sorry, as a reactant, so this would be endothermic, and product side would be exothermic. All right, and that makes sense. You can keep up with that. For instance, I made a fire in my fireplace because I wanted some heat. All right, and so the heat coming out of that is an exothermic reaction. I'm not after the water or the carbon dioxide or even the carbon monoxide that's being produced. What I'm after is that heat that's also one of the products. All right, and so endo and exothermic, we're going to keep up with those. But we'll also be looking at this idea of enthalpy. Now, enthalpy is change is the amount of heat trapped in the bond. But what we really care about is delta H. So instead of enthalpy just being H, delta is change. And it'll be the products minus the reactants. Anytime you see that delta as a change, it means final minus initial. So it'll be products minus reactants. And for us, we're going to keep up with endo and exo. Spell endo today. There we go. So exo, heat is a product, and it has a negative delta H. All right. For exo, heat is a reactant, and it has a positive delta H. In other words, there's more energy in the product side than there is in the reactant side. So when I subtract out the smaller reactant side, I'm left with still a positive number. Where did that extra energy come from? Well, it was added in that extra heat that we added in. All right. In exo, there was more heat trapped in the reactant side than in the product side. And so where did all that heat that used to be in the bonds go? It went out to the surroundings. So what I do is I pick one of these. So I picked XO because honestly, when I was learning this, Beavis and Butthead was still on TV. So we sat around and said, fire, fire, fire. And so I guess you'll have to Google and figure out who Beavis and Butthead are. But so you'll have to know. I'll ask a question. It says something like a blank reaction has heat as a blank and a delta H of blank. And so for an exothermic reaction, then that would be our first blank. And so I might say an exothermic reaction has a negative delta H and heat as a product. And so we'll have combinations of these. Positive, positive, and react. Alright, so exothermic, this one, and endothermic, had a positive delta H and heat was a reactant. And so it's this one. So those are the only two combinations that are acceptable. And so a nice easy multiple choice question. I'll swap up between endo or exo. And the question doesn't have to be changed much more than that. So excellent. So then we're ready for this idea of calorimetry. And this is the process of how much heat is transferred. Now this math seems difficult. It seems complicated, but it's this idea of Q, which is heat. That's a hush talk. So Q is equal to the mass times the change in temperature times C. Now, this is not very difficult math-wise. Change in temperature will just be the final minus the initial. Use a thermometer there. The more mass you have, you should know by now, it takes longer, it takes more energy, it takes more heat to get a big pot of water up to the same temperature as a small pot of water. And then C is specific heat. And it's an idea of how quickly something heats up. And so, there we go. I think that we got him to be quiet a little bit there. So we were talking about specific heat. You already have an idea of this probably, but if you have a large pot of soup and you need to stir it, and you go to grab a spoon, you've got a wooden spoon and an all metal spoon, and you have to choose one to stir it for a couple of minutes. Most people would prefer to choose the wooden spoon because it's not going to heat up as fast. It's going to not get as hot as quickly. It's going to take it long. And so that's the way that we'll be looking at it. And so calorimetry, there's all kinds of different experiments we can do with that. And so for us, what we're focused in is this idea of specific heat, the number of calories to raise temperature by 1 degree Celsius by 1 degree, or 1 gram by 1 degree Celsius. All right, and I'm going to come back and let me just write that down. We want to play with that. Let's play with this idea of calorimetry just for a second. All right. So 1 calorie equals 1 gram, and it's 1 gram of water, and we're going to raise this temperature by 1 degree Celsius, or 1 Kelvin. It would be the same. All right. So if I take a gram of water, which is roughly a milliliter, and raise its temperature by 1 gram, then it would be 1 calorie. All right. We'll also then have this idea of 1 calorie, and you'll notice there's a slight difference between them. This one had little c, this one has a big C, and it's 1,000 grams of water by 1 degree Celsius. Or you could even think of it as taking 1 gram and go up by 1,000 degrees Celsius. Wow, that's a lot of energy. And so I need to think about why do they use this big C and little c? Well, I'll reach over here on my nutrition facts, and it says 140 calories. Oh, wait a minute, you got to be careful. It's not 140 for each chocolate bunny. It's 140 for 1/5 of the bunny. So I guess if I eat his ears, so I guess I've eaten about 1/4 there, 1/5 maybe. So 140 calories. But when I look at that, it's 140 calories, and it's capital C. And they're actually really sneaky. They capitalize everything so you don't notice it's a capital C. This is the same as 140 kilo little c calories. All right, so kilocalories. So it's 140,000 grams of water, and we can raise that temperature by 1 degree Celsius. Ooh, I could take my 1 milliliter of water and raise that temperature by 140,000 degrees Celsius. Ooh, that's a lot of energy. Now, before you start getting worried, well, first off, why do they use big C instead of little c? Nobody would buy it if it said 140,000. It would ruin the chocolate bunny industry forever. All right, and the other thing that is, we need somewhere between 1,000 to 3,000, roughly around 2,000 calories every day, and that's on the big C scale. A little more, a little bit less, depending on how big you are and how big you want to be. So we'll change those up. But we're ready then for our entropy. And so entropy is the amount of disorder, and it's this delta S. And it's really, really tough to measure. And so the free energy, this is a G because it's Gibbs free energy, is the amount this combines the two. And so it has our entropy is delta S, and our enthalpy is delta H. And then this T is the temperature in Kelvin. And so you can see that it has a huge temperature dependence here. And so if it's a positive delta G, the reaction happens by itself. Now, the fact that we have this huge temperature dependence means that many reactions will happen under a lot of heat, but they won't necessarily happen if you just mix them and you don't have a lot of heat. Okay, so not too bad. Kinetics is the study of how fast a reaction goes, and the main term that we need to start off by learning is this idea of the energy of activation. It's the amount of energy it takes to make a reaction go. For instance, the fire behind me is exothermic, but it took a certain amount of energy to get the reaction to start. I've got more than that energy back out of it, but it took a little energy to get it going. Even an endothermic reaction has a energy of activation. So we'll look at that in terms of these energy diagrams. And so here's an energy diagram, and I've got energy versus what we call the reaction coordinate. So the reactants and the products. I'm going to draw this a little bit bigger, maybe a little more colorful. So here's my energy. You can also look at it in terms of enthalpy. All right, both are fine. My reactants would be here, and my products will be this way. All right, and the reaction can either go up and then down, or we might see it go. We can do it in blue. We might see it go up and then down up here. And so that's two different types of reactions. So the blue would be an endothermic reaction, and where we end higher than we started, and an exothermic reaction that we see in the black will be lower than where we started. So labeling these pieces, so let's start with the nice exothermic reaction. So the energy it takes to get to this hump is the energy of activation. That's how much energy it takes. All right, so if I was a big fat ant, the bigger that hill, then the slower I am crawling, even though I'll get lower once I'm to the other side. Now the change from the starting to the bottom, this is my delta H, and we can see that when we do final minus the initial, I'll get a negative delta H. So this is exothermic. We can also tell because the energy of activation is closer to the reactant side. It's always closest to whichever one is higher, and so if it's closer to the reactant side, then this is a exothermic reaction. All right, and so if I can lower that energy of activation, the reaction will go faster and be easier to do. All right. So that's exactly what we need to kind of look at doing. So things that can speed up and slow down a reaction, then we'll be looking at if they're dissociated ions, they react faster. Things in solution tend to react fast. If we have big, large groups, so when you get into organic, a lot of those reactions are really slow because they've got big groups on them. So small molecules tend to react faster. If you raise the concentration, then clearly that's going to go faster. Keep in mind, all of this is based off of the idea that it's when molecules bang into each other. And here they actually have more than just to bang into each other. They have to bang into each other with the right orientation, with the proper speed, all right? And even when they when they hit, then it has to have enough energy to be above the energy of activation. So it's when these things bang into each other. So more concentration, there'll be more collisions between them. Higher temperature means it'll be more likely to have, on average, the energy of activation when they hit. Now this is actually a big one. It says 10 degrees Celsius increase, we double the rate. That means if I do a reaction on a hot day, I'll get a much faster reaction than if I do it on a cold day. All right, so that's going to be really kind of important to us. All right, but gases and liquids go fast, whereas solids go slow. But here's our new big one. This catalyst, this idea of a catalyst. A catalyst increases the speed, and here's the key to this. A catalyst lowers the energy of activation. That's all it does. It's not a reactant. It's not a product. You'll have the same amount of catalyst at the end as you do at the beginning. No more is made, no less is made. Now, sometimes the catalyst gets dispersed into a form where it's not worth our trouble to recollect it. But the catalyst, all it does is lower that energy of activation. And so if I have a reaction that has a high energy of activation, even the delta H will still be the same. All we're doing is providing an alternate path to get to the same place. And so the one in red would go quite a bit faster by having a catalyst. So a catalyst is just there to speed up the reaction. All right. It doesn't serve as a reactant or a product, so it doesn't affect the concentration of either of those. It only serves to lower the energy of activation. So I think we get a couple of pictures of that. Same idea. Some examples, but it's really about the same. All right, so reversible reactions. These are reactions that go towards equilibrium. They don't go completely. And then the key here is this little arrow, and it's a little tough to see on this picture here. So that arrow is a new one for us, and it's a double arrow like this. So it's reaction going to the right and reaction going to the left. And so this signifies an equilibrium. Now we could describe how far the reaction goes. And so in fact in thermodynamics it's regular to look at every reaction as reversible. It's just the ones that we look at go all the way towards the product. And so in reaction that's at equilibrium means that the rate going forward will eventually get to the point where it's equal to the rate going backwards. All right, and so this reaction then, as we make more product, those products will react with each other and go back. And so that's actually what's going on this slide. Is it's describing a reaction which has reached equilibrium. What I'm going to require you to know about it is this idea of what equilibrium is. All right. Now we can describe how far a reaction goes by an equilibrium constant, this KEQ. And so we've got this big formula here for it. So when I see these brackets, so I want to make sure we see those brackets. So if I wrote brackets of Cl minus, this would be the same thing as the moles per liter of Cl minus. Now we had another symbol for that. That was a capital M in chapter 6. So this is our molarity. It's so important that we have multiple ways of indicating it. So then they've taken the C, and those are just our coefficients from our balanced equation. All right, and so we've used them. We just take those directly and plug them in. All right, so this would be the molarity of my N2O5 down here. So notice it's always the products over the reactants, and that's really the only hard part of this equilibrium constant. So what does that mean? Well, if we have a real high equilibrium constant, the reaction goes towards the products. And if it's really big, 10,000, 20,000, 100,000, then it's almost all products. And so the reaction really only goes in one direction. If we get it exactly to 1, the reaction would be the same amount of each side. All right, so anywhere close to 1 is going to be a nice even distribution, and so an equilibrium established between those two. All right, and then if we had this where there's no where the number on the top on the product side is really small, and the product thing on the bottom is really big, then we get something real small, real close, almost to 0, right? So real small, and a real small equilibrium constant, much less than 1, then indicates that the reaction doesn't go forward at all, and that it's very small. All right. So all this discussion of equilibrium constants and might lead you and equilibrium might lead you to think that, hey, we're not going to, we don't have to worry about if a reaction doesn't go forward very much at all, then it's never going to go if it has a small equilibrium constant. Well, fortunately for many of our reactions, we have this idea of LeChatelier's principle. And LeChatelier, oh, that's my favorite word in all of science. LeChatelier. Try saying that with me. LeChatelier. Great word. Favorite name in all of science. All right. So when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. What? All right. So we're going to think of this as a pool of water. Okay. And this is one of these principles that once you get the light bulb to click, it's easy. Until then, it's crazy difficult. So I'm going to sit in the water, and I'm going to take my hand, and I'm going to raise my hand up to the water. So as I get my hand here, there'll be a point where I have this water kind of above. And which way does the water flow? Well, it flows down away from my hand until it fills back in, and I'm left with almost no water on my hand. All right, and so if I start off pushing the water up, it's going to flow away from my hand and back down into the surface. All right. Now, what if I start with my still water and I take my hand above the water and I push down on the water? Well, you'll make at some point an indentation in the water, all right? And then eventually the water will rise, will flow from under your hand back around, and it'll try and fill back in, and it'll come in from all sides. Uh, Matter of fact, we used to push down on water all the time. You'd push down on it, you'd get a big splash up if the water came in fast enough. All right, that's the whole principle behind a cannonball. All right, so LeChatelier's principle says that if I make one side of the reaction go higher and one side go lower. So this idea N2O4, and they tell me it's a reversible reaction, and we get NO2 and two of these. All right, so we're just splitting these up, and if I take this and I take some of this out, so if I make this concentration go down, what that does is it slows down the reaction between this going to form that, because my reactants are going to be lower concentration. And so this speed will still stay the same. And so it will actually start to fill this up because it gets trapped here until it gets back to the point where it was. All right. We could also look at if I raise this one, then this concentration over on this side is much higher, and so the speed going that way will increase, and so I'll get more of it over here, whereas the speed going back is actually small, or going forward would be smaller. And so you can look at it in terms of how it affects the speed by affecting the equilibrium constant by changing those concentrations. But for us, it's much easier to say if I raise this side, the equilibrium goes to the right to make it lower this back down, to get away from this side. So if I lift one side, if I lift this side up higher, it's going to flow to the right. If I come over here and I make this side go lower, it's going to flow to try to fill it in. It'll still go to the right to try to raise this back up. All right. So when we do these, the answers are going to be referred to in terms of shift right, shift left, and no shift. And the things that can affect this, if I change the concentrations, if I change the temperature, and for instance, let's say this side over here has plus heat. So if that side says plus heat, then this would be exothermic going that way. So if I add heat, then I'm increasing this side, and it's going to flow that way. All right. If I reduce the heat, it'll flow back the other way. If I have gases involved, I can change the pressures. Now, gases are really kind of particular because they will only affect if I have the total moles of gas. All right, and so we're just looking at effects on how much gas is there. All right, so these kind of things. So here's an example kind of question. So here's heat plus this. This looks like iron 3 oxide. All right. Oop, I got the wrong arrow, but oh well. And it goes to iron and oxygen gas. All right. So looking at this, this side has the heat. So it says, what is the effect of increasing the concentration of Fe? Now, Fe is on both sides, but when it has just Fe like this, it's talking about it when it's a free element over here. So as we see it here. So if this side goes up, then it's going to shift away from that. It'll shift back towards the left. All right, so if that goes up, it'll shift towards the left. What if I raise the temperature? What if I add more heat? Well, then it's going to shift away from the side that has heat, and it's going to shift to the right. What if I lowered the amount of O2? So I took the O2 out, and if I lowered that, it's going to shift again to the right to try and fill that back up and give us more O2. Notice I only have one side that has gases, so if I raise the pressure, it wants to alleviate that pressure, make the pressure go back down. And so how does it do that? It gets rid of gases and shifts away from that. All right. And so why are these kind of things important? Well, one of the things that we looked at was this reaction between water and CO2, and it uses this double arrow. And when we said that formed H3, I'm sorry, H2CO3, it formed carbonic acid. And we said that when we bubbled away the CO2, when we lowered the pressure, that this went away. And that's because as I take the CO2 away, this shifts to generate more CO2. And so we can taste the absence of the carbonic acid. If I add CO2 and I keep it at pressure, then we had a lot more carbonic acid when we taste it. And so that's actually why we're adding CO2 when we carbonate a beverage. We're looking for this flavoring, not the CO2. It doesn't have a flavor. It's the carbonic acid that we taste. All right. So chapter 7, there's a few major details that we're after. So main idea was this idea of exothermic, endothermic. All right, so make sure you know which one's which. This idea of delta H, make sure you know which one it goes to. This idea of a dynamic equilibrium. We talked about that a little bit last chapter. All right, so I want you prepared just to answer what a dynamic equilibrium is. All right, and I'd also like you to know what a catalyst is. All right, and then I want you prepared to do some LeChatlelier equations. All right, and just tell me things whether they shift left or they shift right. One of the sneaky ones on that, a catalyst doesn't shift it. It has no shift. It speeds up both the reactions going forward and backwards, and so it doesn't really affect the distribution at all. So not a whole lot out of 7, but there's some good key terms in there that we want to keep straight. So a little bit of memorization.